All right, example problem number 1 for setting up Newton's second law. Larry, who has a mass of 90 kilograms, is pushing Ben, who has a mass of 80 kilograms, on roller skates on a frictionless surface. Larry exerts a force of 40 newtons on Ben. After 3 seconds, Larry stops pushing and Ben continues to travel. Sketch the situation, identify the object of interest. Okay, we have the situation sketched, and I'm going to identify the object of interest as Ben here. So I'm going to put a dotted line around him, knowing that he is my system, and then we're going to talk about all the interactions with Ben. Alright, so Larry is interacting with Ben. The Earth is interacting with Ben. Wow, that's the worst E I think I've ever drawn. And the floor is interacting with Ben. And the floor is pushing up because it's, in this case, it's a support force. There's no friction because the problem states there's a frictionless surface. Alright, so next what we're going to do is we're going to draw a motion diagram and a force diagram. Well, for the first 3 seconds while Larry is pushing, Ben is going to get faster. So V1, that velocity arrow is going to grow in size, V2, V3. We have our change in velocity going to the right. And after he stops pushing, since the surface is frictionless, Ben should then travel at a constant velocity until an external force slows him down. Alright, during that time we have our force diagram. We have the force of the floor pushing up on Ben. We have the force of the Earth that is pulling down on Ben, and we have Larry pushing to the right. On Ben. Alright, so on the page now you have 3 things. You have what's denoted as positive x and positive y direction. That's right is positive x and y is up. You have Newton's second law written for the x direction, and you have Newton's second law written for the y direction. So this is what we mean by component form. We draw it out horizontally, we write it out vertically. Alright, so now we're going to apply this. Since Larry is pushing to the right, we have the acceleration in the x direction will equal to the force of Larry on Ben divided by the mass. Everything goes in variable form first. Alright, we look at the force of the floor and the force of the Earth. We know that the acceleration is directed to the right, not up and down. So in for AY will go 0 meters per second per second. And then you would have the force of the floor on Ben minus the force of the Earth on Ben, and divided by the mass of Ben equals 0. Alright, once you've written everything out in variable form, you can then substitute numbers in. So we know the force of Larry on Ben is 40 newtons, and we know Ben's mass is 80 kilograms. So we can calculate the acceleration is 0.5 meters per second per second. And since they asked nothing in the vertical direction, we can just leave this as is. Now, once Larry stops pushing, that force exerted by Larry will cease to exist, and he will continue moving on, as we said before, at a constant speed. So he will not have any acceleration. His velocity will not change. And then F is finds Ben's velocity after 3 seconds, if he started at rest. So this is kind of a little reasoning thing here with acceleration. If initially the speed was 0 and he accelerated at 0.5 meters per second, that means after 1 second he'd be traveling at 0.5 meters per second. After 2 seconds, he would then increase another 0.5 meters per second and be traveling at 1 meter per second. Then after 3 seconds, he'd be traveling 1.5 meters per second. Again, the same increase of 0.5 meters per second each time. So this is example problem number 1, and we are done.